let us start with the basics of federated learning. I think even Anis, everybody has like sufficiently discussed what federated learning is, but just to provide a quick recap, federated learning is a privacy-preserving training in massive heterogeneous networks. And what are the basic properties which a federated learning system should satisfy? We should be able to tolerate low participation of the nodes or agents or devices, whichever we want to call them, or clients. And we should be able to provide a user privacy so that the model do not send their raw data as motivated by Jihong in the previous talk. And the devices should be allowed to be heterogeneous, or they are indeed heterogeneous, and we should take care of that fact while designing algorithms. And specifically because the number of devices is too high, generally the communication is expensive and between the server and the devices. So we should somehow like focus also more on the doing local updates, less server updates. And there are different types of trade-off between them, and then how to understand or how to play those trade-offs to develop efficient algorithm. That is in nutshell the whole problem or the area of federated learning is. So mathematically speaking, we can formulate the federated learning problem as we want to minimize a function f of w, where w is the parameter or the optimization variable in mathematical terms, and is generally given by the sum of capital N number of loss functions, where fk denotes the loss function of each device and pk is the corresponding weight of each device. And generally we assume pk lies between 0 and 1, and the summation across all the devices is just 1, so that we have like it behaves as a weight factor towards the local loss function of each device. And one example of this could be, one example of this specific function is nothing but just summation of all the local data samples and specific instantaneous loss function. And we want to minimize this sum and to find this parameter w. So how to do that? What is the basic workflow of federated learning? We start with the device selection. There are different kind of device selections we can deploy in our algorithm. For example, it could be random device selection, weighted device selection, event trigger, or we can also select according to the fairness, or if we want to introduce fairness into the system. So there are different ways in the literature to do the device selection. And once we select the device, when we do the device optimization, where we run the local updates from the local data to update the local parameters, and different algorithms are examples of that: FedAverage, FedProx, Scaffold, MIME, and FedDyn. And then once we have done the local updates, we aggregate all the local models at the server, where we can do different type of averaging. Naive averaging is just take the sum divided by the total number of devices. We can do weighted averaging or FedNova. Different kind of approaches are available. We can pick any of them depending upon the application or problem of interest. And then additionally, if we have additional budget at the server, we can perform additional optimization at the server to improve the overall performance or overall estimation of the global model. So the state-of-the-art algorithm, I think we must have like talked about it multiple times, but I'll just provide a quick recap of federated averaging algorithm. This is a very simple algorithm where we run different local SGD. SGD means stochastic gradient descent updates at each device. And once those updates are done, we just share the local updates at the server, take the simple average, share the global update again with the local devices, and keep running this algorithm again with the hope that eventually the global model will converge to some value. However, this algorithm can diverge also when there is a significant statistical heterogeneity across the devices. By heterogeneity means the data is coming from different distributions across the devices. And this algorithm also lacks theoretical guarantees when it was proposed, but in the recent literature, people have tried to work out its theoretical guarantees and provided under different assumptions. As a quick empirical evidence to show the divergence of Fed average, we can see that for different epochs, the training and testing performance of the Fed average algorithm is not very good in Shakespeare dataset, which is highly heterogeneous, and the same behavior we can observe in other datasets as well. So there are different issues. But this issue of heterogeneity was first resolved by this idea of FedProx, where the authors have proposed that instead of just focusing on minimizing the local loss function, let us introduce a proximal term, or you can say like additional augmented term towards the objective, which says that our local model not only just minimize the loss function, should also be at its distance to the global model should also be minimized at the same time. And then they put mu as the penalty parameter or the proximity parameter for this penalty or for this regularization term into the local loss function. And what it does is it just tries to keep our local estimate close to the global estimate. And they have shown in the paper that it results in better convergence, even if for heterogeneous data sets, even if the Fed average was diverging, but it starts converging. But it introduces an additional challenge of this tuning additional parameter mu, or we can say hyperparameter mu, which we generally don't know in practice, and we do it by cross-validation. So Fed average was there, then FedProx came. So we took another step ahead and then say that what could be the generalized version of this FedProx, and if there is anything we can do. One thing to note here is that in Fed average and FedProx, in both of the cases, the averaging step at the server is still the standard averaging. Like we collect all the local models, simple, just take the sum divided by the total number of devices, and we consider that as our new global model and send it back to the devices. But we propose, or we try to introduce this idea of like going beyond consensus. By doing that, simple averaging is nothing but just trying to force the global model to converge to the local model for each devices, or in other words, try to satisfy the consensus constraint. And then what we say is like, let's just see what happens if we do not try to satisfy that consensus constraints and try to go beyond that. So to conceptualize the idea or to understand it, let us try to look at the same problem. We want to minimize the sum of loss functions, but here you see that I just changed the notation a bit. Instead of W, we will call it Xi. Instead of just W or single X, now each X has its index I. So it is a device specific. And now this constraint is there, which is saying my local model should be equal to a global model Z for all I. And this is called consensus reformulation of the federated learning problem. And we can write a primal-dual algorithm and it will exactly boil down to federated averaging. And actually that averaging step at the server is coming because we want to satisfy this equality constraint. And we take a step further and then say that instead of satisfying this constraint with equality, let us try to satisfy it with inequality or introduce this additional parameter, which we call a personalization parameter, which says that instead of forcing my local model to be exactly equal to my global model, we would say that my local model should lie in an maybe square root gamma I epsilon ball around the global model. And once we add this additional freedom, what happens, what kind of benefits we can get, or like what kind of trade-off this parameter introduce into the formulation. So this introduction of gamma I is actually making our whole idea of federated learning going beyond consensus. So we simply write the Lagrangian. Don't worry about these details, but this is just like the mathematical way of deriving the local and the global updates. Eventually what happens is we just get the standard SGD updates for the local model. And for the global model, interestingly, what happens is our standard averaging gets replaced by the weighted averaging. And even more interestingly, those weights are not just any random number, they are actually the dual variables which controls or which actually looks at how much my constraint has been satisfied and accordingly adjusts itself. So our standard federated learning algorithm automatically becomes an algorithm where we have now weighted averaging at the server, and the weights are automatically adjusted by the dual variables through this concept of federated learning beyond consensus. So interestingly, what happens is all the existing algorithm like Fed average, Fed prox, Fed PD, all are special case of this federated learning beyond consensus framework. The only thing we need to do is in this whole objective, if we make lambda I 0, it exactly boils down to Fed averaging. If we make lambda I equal to a constant mu, it boils down to Fed prox. And if we make gamma equal to 0 and do no device sampling, it boils down to Fed PD. So this federated learning beyond consensus framework or the problem is generalized enough so that it covers all of the existing algorithm as special cases. And it works in practice. Before showing the experimental results, let me quickly describe the convergence analysis or the convergence results of the proposed federated learning beyond consensus algorithm. This is the global convergence results, which says that now, like running average or the average value of the global gradient is nothing but of order 1 by t. This is the initialization dependent term and will go to 0 as t tends to infinity. And the second term is order epsilon, where epsilon is the accuracy of the local device. Delta square is the heterogeneity parameter. Alpha is the step size. And this last term is a new term which appears in the analysis of federated learning beyond consensus. And here you can see it depends upon gamma I and capital N. And gamma I are again the new parameter we introduce into the problem. And if gamma is equal to 0, then it again boils down to the standard federated averaging convergence rate. And instead of just focusing on the global rate, we also derived a local convergence rate. The difference you can see here, it is the grad f. There is no I here, but here it is like agent specific gradient. And what is the average value of that? It depends on the local accuracy and the amount of constraint being violated, which makes sense. So experimentally, we performed on synthetic as well as real data sets. And for synthetic dataset experiment, we use the FedProx paper setting and then try to generate this synthetic data set. And these are the results. We compare the proposed FedBC algorithm with all Fed average, FedProx, and scaffold. So let me try to explain it even in more detail. What is happening in this figure is due to this phenomena of like learning beyond consensus, we observed an interesting like phenomena happening in the algorithm or in the performance is like it automatically introduces fairness into the learning procedure. By fairness, we meant the orange dots in this figure shows the max user. The max user means because there is a heterogeneity in the environment, max user means the user or the device with the highest number of data points, and the min user or the blue dots means the device with the lowest number of data points. And generally, the existing federated learning algorithm suffers from like an implicit bias, like they're biased towards the max user, which has a high number of data samples, and different kind of techniques are proposed in literature to deal with this unfairness in the model learning. But interestingly, you can see that in FedBC, as the number of rounds are increased, the performance of the min and max user are equivalently increasing. And this gap here shows the benefit, while in all other approaches, you can see the presence of these blue dots in this area shows that they are not that fair in terms of learning a global model as FedBC is. And this was not the aim to start with, but this comes as a byproduct of introducing the idea of federated learning beyond consensus. And it still requires additional investigation, like what else lies beyond fairness in the idea of federated learning beyond consensus. And this is the first result we obtained. And why that is happening, how it is different from the standard Fed average based techniques, or like instead of that dual based weighted averaging, if we just use like data size based averaging, like if which is generally used in the literature, because data size generally we know, if we know the data size, we can accordingly give the weight to each device and then accordingly do the averaging at the server. And we can see that in this left hand side figure, this blue dot and orange dot are the like min device and max device weights for the data size dependent min max averaging, while on the other hand, this solid green and solid red are corresponding min and max user weights for the proposed technique. And you can see that the green and red one are becoming closer to each other as the round size increased as compared to blue and orange one. And that is the reason why there is a benefit in terms of fairness achieved by the proposed algorithm. And this right hand side shows the weight distribution with respect to the data size, like the devices which have highest number of data size, they have the higher weight, and the devices which has low number of data sizes, which are more, have lower weights. But in the proposed technique, it gives is some sort of like uniform distribution of the weights automatically to each device. And that is where the benefit of fairness is coming from. And we also show the experimental evidence or benefits on real data sets like CFAR10, Shakespeare's and others in the paper. And here it clearly shows benefits as compared to all the existing techniques. And this shows the different weights distributions of the proposed algorithm. So in summary, we have introduced this new idea of like going beyond consensus in federated learning. And high-level idea is, instead of pushing our global model to be exactly same to each local model, let's try to give it little more freedom in terms of how my local model can behave with respect to global model, and see if we can get new benefits from that additional trade-off. And instead of that, there are additional open questions about federated learning validation and testing, and how to measure the performance of the model across devices. That is still not very well established in the literature. Or how to personalize for a device which has too few samples, which is of very much importance for medical applications where there are small clinics which have very less number of samples, but as compared to big hospitals. And how do we define personalization or personalizability for them? And if we can't personalize at a device level, what is the right cohort size and subspace to personalize at that level? And another interesting open problem is like PAFL in the face of no labels, and federated version of self-learning and semi-supervised learning are additional interesting directions. And I'm happy to talk to anyone interested to work in these directions and brainstorm further. Thank you so much for your time and listening. I hope I'm happy to answer any questions. Thank you so much.
Yeah, Amrit. Hi.
Hi, Anis. How are you?
Good. This reminds me of a paper under the title, if I'm not mistaken, Personalized Federated Learning.
Yes.
Yeah, where actually, if you go back to your formulation, if you go back to the formulated problem, they introduced a quadratic term plus mu I.
This one?
Yes, this one. Yeah, go to that one. So yeah, what you did, because for every, here, just replace mu with mu k, then for every gamma k in your problem, there is a choice of mu k that matches that, right?
Yes.
So then there's a big similarity between. So what's the difference then between your problem? Because it seems to me it's the same problem, right?
Yeah, problem is same. It is coming from like Yeah, okay. So if you make this mu as mu k, and then I think it is the way you choose mu k. If you keep it free as a hyperparameter, then I think it matches with what you are describing, but we are trying to control it through the dual updates automatically. We no longer need to train it, or like it is no longer a hyperparameter.
And for the FedBrox, if you go back, actually in FedBrox, the quadratic term is not part of the problem formulation. It's introduced in the algorithm in order.
Yes.
Yeah. So actually, in that sense, then FedBrox is not personalized.
Yeah,
framework.
FedBrox is not personalized, and our idea is also not like to develop a personalized solution that it will come as a byproduct, but we are still interested in training still the global model, which is which performs good like for all the devices. But like going into personalization makes it a little more complicated. We have even tested its performance on personalized models, but it does not work better as compared to, say, per Fed average or like whatever the personalized algorithms, because they care more about the personal models. Their global performance is bad. So there is actually a tussle or a trade-off between the global model performance and the local model performance. So for this thing, we are mainly focusing on the global model performance. For local model, we need additional fine-tuning steps to make it like match with the state of the art.
And the choice of gamma I is very tricky here because it depends
on that's for sure. For experiments, we run an additional SGD for gamma I to like for the algorithm to let it choose it on its own, and that works really well in practice. But theoretically, justifying that step selection is very difficult. So theoretically, we keep it constant, but for experimentally, we define a loss function with respect to gamma as well, because ideally, we want the constraint to be as large as possible so that each device has its own freedom of selecting the model. So, defining that as a loss function with respect to gamma and running just one SGD, that works really well for all the experiments for our case.
Okay, thank you.
Yeah, thanks.